All right. Here we are for AP Physics pendulum problems. We're going to do problem 3. It says, a particle of mass m slides without friction inside a hemispherical bowl of radius r. Show that if it starts from rest with a small displacement from equilibrium, the particle moves in simple harmonic motion with an angular frequency equal to that of a simple pendulum with length r, okay, whose length is the same as the radius of the bowl. So let's draw a little sketch, okay, for that problem. Problem 3 here. Okay, now I have this hemispherical bowl. All right, so maybe there's like, you know what I'm saying? Okay, and we have this this particle that it says is slides without friction inside it. That it starts from rest with a small displacement from equilibrium. Equilibrium would be if it was sitting at the bottom, right? That's where everything would be balanced out for it. So we're going to take this particle, whatever it is, and we're going to displace it from the equilibrium position by some little bit. There it is. Okay. And so then it's going to slide downhill and then slide back uphill. It's going to go back and forth and back and forth. Again, that's that distance r again, right? The radius of the bowl, mass m. And they want us to show that it moves in simple harmonic motion. So I'm going to do my little force diagram here. You can say for that particle, I would have a gravitational force down, and I have a normal force from the surface of the bowl. And it's sliding without friction, so that's it. That's our forces. You can see right away that I'm going to have, if I think about radial and tangential, that radial, tangentially, I'm going to have a tangential acceleration from mg downward, which is good because it's supposed to slide down, right? So when I take a look at this, you might say that this part here, if I call that theta, this would be mg sine theta. That's the force that's really pushing it back towards equilibrium, is mg sine theta, right? So I know that as I change angle, then that force is going to change. It's proportional to sine theta. But what I would like to do is I'd like to, rather than do that, okay, I'd rather think about this because they want me to compare it to a pendulum. So I'm going to derive it the way that I derive the equation for a pendulum. I'm going to think about angular quantities, okay? And I'm not going to think about, this component. I'm going to think about the torque caused by gravity. So I'm going to go ahead. I'm going to do sum of the torques is I alpha, okay, which is how we analyze rotational problems. This is just going to be the only force to do torque, R cross F, is with gravity. So doing R cross F, V big R, my force is mg times the sine theta, whatever angle I've been displaced through, is going to be equal to I alpha. Now, I, for particles, remember we're treating this as a point particle. This is going to be our axis of rotation. We're thinking about it, changing angle with respect to that point, right? You know what I mean? So that's our axis of rotation. So I'm going to say that's just point particle. I is the sum of the mr squareds. So I've got my mass m, and my radius is just the radius of the bowl, mr squared. So that's what's going to go in there for I, which will go here. That's sloppy. Mr squared. And then alpha. Alpha is the second derivative of theta with respect to time. I can see the m is going to drop. One of the r's is going to drop. I'm going to end up with g over r sine theta is the second derivative of theta with respect to time. You say, I know that if technically if this is theta is 0, this is a negative theta displacement, and I'm getting a positive torque trying to go the other way. You know what I mean? If this is the negative direction, the torque for this r cross f is the other way. So the sign's going to be flipped. Okay, is the simple harmonic motion a pattern? You say, no, I remember the simple harmonic oscillator pattern is negative a constant times my position is equal to the second derivative, the acceleration, the second derivative position with respect to time. I have negative, this is a constant, but I've got sine theta instead of theta, instead of angular position, right? Angle is second derivative of that. If only this was theta, it would be that pattern. And this is where you pull out, wait a minute, sine of theta is about equal to theta. For small angles, that's the small angle approximation for sine. Okay. They told us in the problem specifically that it starts from rest with a small displacement from equilibrium. So we can say good enough. So that becomes sine theta. So I got negative g over r sine theta is the second derivative. You say, now wait a minute. You say, oh, except I've made that just theta. Whoops. That was the whole point of what I just talked about. Okay, and that is the simple harmonic oscillator pattern. So we've shown that it's going to be a simple harmonic oscillator. It shows that pattern. And we know the period, you know, the coefficient here on the position, that's the omega squared. And so rearranging this then, omega is the root of g over r. My period for simple harmonic oscillator is 2 pi over omega. So the period is going to be 2 pi over the root of g over r. Sure, why not? So again, reciprocate, put it up to the top. My period is going to be 2 pi root r over g. Hey, so that's what I got for this ball in the bowl, or particle in a bowl. That's the formula for its period. You say, what about a pendulum? Well, the formula for a pendulum is 2 pi root L over G, right? In this case, the length of the pendulum is R. And look, there's the same formula. Okay, and that's what I was asked to show. Yep, good enough. They got the same period. I'm actually meant to show they have the same angular period, but I'm sorry, the same angular frequency, the same omega. But omega squares g over r. We know that for mass for a simple pendulum, it's g over the length, right? And the length here of a pendulum, they said it's a pendulum with a length r. So, yep, you get the same thing out. All right, that's problem 3.